Hey calculus class, welcome to second semester. Today we're going to learn topic 47, solutions to differential equations. So first we have to define a differential equation. So a differential equation is an equation that contains an unknown function y and one or more of its derivatives, so y prime, y double prime, etc. So the order of a differential equation is the order of the highest derivative that occurs in the equation, just like polynomials. So if I have xy plus y prime equals 2, that means I have a first order differential equation. If I have y double prime times y minus x over y prime equals -9, that means I have a second order differential equation. A solution to a differential equation is a function such that y equals f of x that satisfies the differential equation in question. So for example, if I have the differential equation x times y prime plus y equals 2x, and that a possible solution is y equals x minus x to the -1, the way that I would determine if this was an actual solution to the differential equation is I would have to substitute in y into the differential equation and y prime and see if I get the two sides equal to each other. So I already have what y is. Y is x minus x to the -1, so I can plug that in for y, but I need y prime. So I'm going to take the derivative of this possible solution first to find y prime, which will give me 1 plus x to the -2. Now I'm going to go ahead and substitute in y prime and y, and I'm going to simplify to see if I get this left-hand side to equal the right-hand side. And after simplifying, I do. I get 2x equals 2x. So therefore, I can conclude that y equals x minus x to the -1 is a solution to the differential equation x times y prime plus y equals 2x. A separable differential equation is a first-ordered differential equation where one side can be split up into a function of x and a function of y. So, for example, if we have dy dx equals g of x times f of y, or dy dx is equal to g of x over f of y, where of course the denominator can't equal 0, we want to separate the variables so that one side is in terms of x and the other side is in terms of y. So to do that for this first one, I would divide both sides by f of y and multiply both sides by d of x to get 1 over f of y dy equals g of x dx. And then for the one where it's a quotient, basically I would cross multiply. Multiply both sides by f of y, multiply both sides by dx to give fy dy equals gx dx. So in order to get the solution, you will need to integrate both sides. So for this one, I'm going to integrate, and then same with this one. So let's do some examples. For each one, we're going to find the solution to each differential equation. And they're all going to be first order. In this class, we only work with first order differential equations. When you get into college, after multivariable calculus and linear algebra, there are classes specifically designed for differential equations. They're actually called DiffEq. So if you want to go into deeper differential equations, you would take a separate class that focuses just on DiffEqs. All right, so we want to find the solution to dy dx is equal to e to the 2x over 4y cubed. So the first thing I'm going to do is get one side where all the y's are and one side where all the x's are. Then I'm going to integrate both sides. So on the left-hand side, I'm going to integrate in terms of y, and on the right-hand side, I'm going to integrate in terms of x. So for the right-hand side, I'm going to do u substitution. So my inner function is 2x. So my du is 2 dx. So I'm going to have to substitute in the right a 1/2 du. And when I did that, I also integrated the left-hand side. And for this, you have to remember your plus c's on both sides. And so to differentiate between the different constants, I have plus c sub 1 for the left-hand side. Now when I integrate the right-hand side, I'm going to have a plus c sub 2. Now I'm going to solve for y, because that's what the solution is going to be y equals the function. Now, of course, not all of them can be solved for y. So if they can be solved for y, solve for y. If they can't, do as much simplification as you can. All right, so when I subtract c sub 1 on both sides, that means I'm combining a constant with a constant. So that means a constant minus a constant is another constant. So to differentiate between all these constants, I'm going to let the final constant be k. So now I have y to the 4th is equal to 1/2 e to the 2x plus k. 4th root both sides, and since it's an even root, I got plus or minus. So this would be my solution to my differential equation. All right, why don't you try this one on your own? All right, let's see how we did. So you had to separate the x's and the y's. So divide by y squared, multiply by dx. Integrate both sides. And after integrating, you would get negative 1 over y. And I got this because I brought y squared to the top to get y to the negative 2. And of course, the antiderivative of sine x is negative cosine x. Subtract the constants. So now I get negative 1 over y equals negative cosine x plus k. Basically, cross multiply on both sides, solve for y. And I can pull out this negative, and the negative cancels. And the reason why this does not become a negative k is it's because it's a constant. So if you have plus a constant, if the constant's negative, it will work itself out. All right, now this one, when the variables are not x and y, which variable goes on which side? So basically your goal will be to solve for the variable that is on top of the derivative. So in this case, it's going to be z, because in the previous ones we had dy dx, we solved for y. Now since we have dz dt, z's on top, I'm going to solve for z. So notice this time I have everything on the same side. So in order to get variables on different sides, I'm going to have to subtract the e to the t plus z. Now to separate the variables, I'm going to need to use my exponent properties backwards. So I can rewrite e to the t plus z as e to the t times e to the z. And now I can separate the variables. I get z on one side, t on the other side. Integrate. And in order to do this, I'm going to bring up e to the z as e to the negative z. Pull out that negative 1. Now at this point, you can go ahead and integrate. You would have to use u substitution here. And since I'm going to have to use u substitution here, and I know that the derivative of negative z is negative 1, I have a negative 1 over here. So I'm actually going to bring this negative 1 over here so I don't have extra negatives. Technically, you don't have to do this. Everything would work itself out if you left the negative where it was. All right, I can now go ahead and do u substitution on the left-hand side. So my inner function's negative z. So my du is negative dz, and I already have a negative sign, so I don't have to worry about that. So now when I resubstitute in, I now have e to the u du and e to the t dt. Integrate both, resubstitute in u, and I'm going to solve for z. So to do that, I'm going to subtract the constants, get them on one side. And since I have e's, in order to get the exponents down, I have to natural log both sides. Notice I have absolute values when I natural logged both sides. That's because we don't know the value of k, so we must use absolute value to make sure that the argument will be positive. So that means on the left I now have negative z equal to the natural log of e to the t plus k, and then get z by itself. And we have our solution to our differential equation. All right, now let's look at one where you actually have to solve for that constant to get a specific differential equation. So in this example, notice that we are given an initial condition. So when we solve for our constant, we're going to have to use this. All right, so notice here I have y's on top and the bottom. So I'm going to have to do some algebra to get y's on one side and x's on the other side. So I'm going to start off by cross multiplying and then dividing by y to get all the y's on one side, and then multiplying by dx. So now I'm going to go ahead and integrate. So in order to integrate the left-hand side, I have a single term on the bottom, so I can split it up into two fractions to get 1 over y plus y dy. And now I can go ahead and integrate. Antiderivative of 1 over y is the natural log of the absolute value of y. Antiderivative of y squared plus 2 plus my constant. And antiderivative of cosine is sine. So now I can go ahead and get my constants onto one side. Now at this moment in time, I would go ahead and plug in my initial condition for x and y and solve for k. And the reason why I would do that now is because we kind of can't solve for y. We have y's inside logs and then outside logs. So that's why I would go ahead and solve for k now. So I put in 1 for y and 0 for x to get that k will equal 1/2. So now I can write my final solution as the natural log of the absolute value of y plus y squared over 2 equals sine x plus 1 over 2. Well, I hope you enjoyed learning about the solutions of differential equations, and we will practice these more in class tomorrow. Have a good night, and see you tomorrow.